Now that we know the Gilbert-Southwell theorem and its proof, let us try to ideate and brainstorm a little bit about why this result holds. What is the intuition behind the very restrictive result that if you want to satisfy these two important properties, onto-ness and strategy proofness, and if you have three alternatives or more, all the social choice functions must be dictatorial. Now, one of the things that you can immediately see is that we are using this preference profile here. So the preferences that these players can pick can come from all possible preference orderings. So if you think about three alternatives, there are 6 possible, so 3 factorial, that is 6 possible preference orders among them: ACB, BAC, BCA, CAB, and CBA. So what the Gilbert-Southwell theorem is saying, that player preferences can be any of these preference orders over this m alternatives. In particular, if there are m alternatives, there should be m factorial such preferences. And this result is holding because a potential manipulator has many options to manipulate. So if somehow, let's say, we could have restricted this the number of preference profiles to a subset of it, maybe something like this, then all the social choice functions which were strategy proof here would still continue to be strategy proof in that smaller domain, but maybe we can actually have more social choice functions which satisfies this. What is the reason for that that intuition? So for that, let us look at the condition of strategy proofness more closely. So we have this, so what does strategy proofness say? That if we have this preference, player I has this preference ordering PI, then if the player reports PI truthfully, and other players can report whatever they want to report, and they should always be better off by reporting it truthfully rather than reporting something else, which is PI prime. If this, so what can happen? Either they prefer the current outcome from any other outcome, or the outcome might not change at all. So in these two cases, we will call that this mechanism is strategy proof. Now you see that this is a set of statements, logical statements, which has to be true for all PI and PI primes in the script P. Now if we make this the space of all possible preferences from this script P to something smaller, which is a strict subset of this preference, then all the conditions that we have here for a specific F which is strategy proof will continue to hold, but maybe there are some new Fs which will also start satisfying those conditions. And that is the intuition why we can restrict this preference profile and get some more positive results. So as an extreme case, if you have only one preference profile in this space, then you know that this is immediately strategy proof, because the players cannot manipulate to anything else because they do not have any other choice. So that restriction, so that is what we are going to call as the domain restriction. So the domain of the social choice function is getting restricted, and that may give us, and we'll see a few examples where we can get more social choice functions which are strategy proof, which are also non-dictatorial. So we don't want to use the dictatorship that becomes very degenerate mechanism. So in this course, we are going to discuss about 3 different domain restrictions. The first one is single peak preferences. The second one is when we have the setting of divisible goods allocation, and the third one is of quasi-linear preferences. All of these are applicable to several certain settings which are quite reasonable in practice, and also we will show that it has some interesting non-dictatorial social choice functions which are also strategy proof. Let's begin with the single peak preferences. So as the name suggests, it says that there exists a single peak in your preference. So let us start with an example to understand this point. Suppose you want to set the temperature of a room by asking every agent what is the most favorite temperature, and the most comfortable temperature is something like a single peak. So you can imagine that all the temperatures can be ordered with respect to the linear order. So maybe 22, 23, 24 and so on. All these temperatures are, this order of the temperatures are the same. So 24 is greater than 23 for all the agents. So that is one common ordering that we have. Now maybe someone has the most preferred temperature as 24. So anything colder than this is not so preferred. Anything hotter than this is also not preferred. So in some sense you can think that the preferences are going down in both directions. So this is the most preferred temperature. Anything beyond that is going to be strictly decreasing in both directions. We might not say what is the relative ordering between this and that. So it may admit, so maybe you prefer colder temperatures more than hotter temperatures. So in that case this will be above this alternative. 23 will be above 25. But that is perfectly fine. In fact, 24 followed by 25 and 23 is also admissible. But the point is that there should only be a single peak, and hence the name single peak preference. So maybe this is the preference ordering for player 1. Similarly for player 2, maybe you can have a different preference order. So maybe this player 2 likes a different temperature as its most preferred temperature, and it also has a single peak around that. And that is exactly what we have drawn here. So player TJ has a different peak, player TI has a different peak, and these are the temperatures that they like the most. And so that is an example of how single peak preferences look like. So what are the important parts here? So there exists one common order, as we said. So here the natural order over this alternative. So how can we cast this into the social choice setting? So suppose we collect these preferences, which are single peak preferences, the temperature preferences of all the players, and we were going to set our the temperature of our air conditioner to that particular temperature, to some particular temperature. So the outcome, the alternatives, can be one of these temperatures here. And what we notice here is that there exists a common underlying order of all the alternatives, which is the real number ordering over these temperatures here. And for single peak preferences, these preferences are having a single peak for every player with respect to this common order. So this actually makes a bit of restriction. We'll see that very soon. So there are other examples of this kind of single peak preferences. So the first example is that of facility location. So suppose for simplicity, assume that the city is something like a real line, one-dimensional city, and you have a facility. So maybe player I has his house here and player J has her house here. And suppose if there is a facility like a school or a hospital, they want that to be located as close to their home as possible, and the preferences fall on both sides. So if they are farther from their location, the preferences are going small, and the similar thing is true for player J as well, right? So that is also an example of a facility of a single peak preference. There could be other examples. If your ideology is a left, center, or right, then maybe you have three preferences, and if your ideology is left, then you like that over center over right, and if it is right, then the reverse implication holds. So for the purpose of this course, we are going to use this notation, this strict less than notation, as we use in the real numbers as the natural ordering. So we will say that L is less than C less than R. So this is the common ordering over the alternatives, and that is something that we will always assume, even though we do not explicitly write it. That is always there in the single pick preferences. So just to summarize, we have the alternatives which has a natural ordering which is common to all the players, and now over these alternatives people may have different preferences. Now let us look at why this is a domain restriction. What are the things that we cannot have in the single pick preferences? So in general, you can have this relation, this natural ordering over these alternatives to be transitive and antisymmetric. So antisymmetric means that if A is above, so A is less than B, or you can have B is less than A, but you cannot have both of them to be true. So this is the natural property of this ordering of the real numbers. So they are transitive and antisymmetric. So for this course, we are always going to assume that these alternatives are living on a real line, so that we use this notation to denote their natural ordering. And also we are going to consider only one-dimensional single pickness. So you can think of that you have a two-dimensional space, and the preferences are something like a conical shaped preference. So you have a pick somewhere in this two-dimensional space, and it is uniformly falling from that point. But we are not going to consider that kind of a preference profile in this case. We are only going to have a two-dimensional projection of that. So we have one single real line, and on top of that the preference is a single pick. Now let us come back to this question of why this is a domain restriction. So what cannot be admitted in a single pick preference? So let us consider that this single picked, the common ordering over these three alternatives. Let us consider there are only three alternatives, A, B and C, and they are commonly ordered on this real line in this way. So then what cannot happen is that A or C is at the top. So let's say C is on the top, and A is the second most preferred alternative. That is not possible, because then what happens is you have two picks, one pick here, one pick here. So with respect to this ordering ABC, right? So that is actually ruling out some of the possibilities which was possible in the complete domain, that script P. So look at the previous thing. We had all possible, here we have enumerated all possible m factorial preference orders over these three alternatives, but here we can see that you can have A over B over C, that means this, B over A over C, so B is the pick and A the next and C is the last, or B is the pick and C is the second highest and A is the least preferred alternative, or it can have a C, B, A. So that is also feasible, but you cannot have alternatives like A, C, B. So A is on the top, C is the second top and B is the last one, or CAB. So C is the top and A is the second top. That is not possible. So these two things are actually ruled out. So in script P, all of these were admissible, but in script S, which is the single pick, only these are admissible if the common ordering over ABC is this. If you change this common order, let's say B is now less than C, C is less than A here, then this preference orderings will also change, but again you will have two alternatives which are not feasible in that setting as well. So let us say this a little more formally. So we will say that a preference ordering PI is linear over A for agent I. So we are only going to consider linear orderings as before. We call that to be single picked with respect to the common order less than of these alternatives if two conditions hold for all the pair of alternatives B and C, such that you have the pick. So you pick one of the topmost alternative for player I, and let's say this is happening. So B is less than C and C can be less than or equal to the topmost alternative, then it must be the case C is more preferred than B. So what it says is that you have PI1, which is the topmost alternative for player 1, and B and C are ordered in this way. C is here, B is here. So then C must be more preferred than B. So that is one of the restriction of single pick preference. Similarly, if you have this lies on the right hand side and B is still less than C, then it must be the case that B is more preferred than C. So this is the second condition. So that is the formal definition of a single pick preference. And we are going to consider the social choice function that maps only this kind of preference profiles to the set of alternatives. So look at this S. This is now a strict subset, and therefore this social choice function is a domain restriction of the original social choice function. Now, since we have said that this is an interesting setting with many applications possibly, how does it circumvent the GS theorem? So let us look at one specific example. So let's say what we are going to do. So let's say we can go back to the temperature setting example here. So let's say some player has T1 and some player has T2. So T1 is above, so T1 is smaller than T2, and let's say T3. So this these are the different peaks of these players. And now we are going to collect together all the picks. So let's say here is my social choice function. So we collect all the picks of all the players. We ask everyone what is your most favorite temperature, most comfortable temperature, and we are going to pick the median of most favorite temperature. So in this case, T2 will become the outcome. So the temperature with which the AC will be set is T2. Now let us look at why. So this is clearly not a dictatorship, because once this pick changes, the outcome will also change. We are not always picking the same player's outcome. So let's say T2 is player 2's most preferred alternative, but if player 2 has an alternative which is, let's say, T2 prime, which is smaller than T1, then T1 will be the outcome, because that is the median, the new median here. So clearly it is not a dictatorial one. Let us see why it is strategy proof. So if player 2 has this peak, and that is going to be the outcome of the median. So if the player itself is a median player, then it has no reason to manipulate, no reason to report its peak to be something different, because it is getting what it prefers the most. For player 1, what is happening is its preferences are falling in this way. Player 1 likes a more colder temperature, but of course what is currently being set, which is T2, is more preferred than T3, that is much more hotter. So the only way player 1 can change this outcome is by reporting its peak on the other side of this median. But clearly that player 1 prefers that even less than the current outcome, which is T2, right? So any other outcome, so player 1 will not manipulate, because by manipulating, what you will get is essentially worse than what he is getting currently. And you can see that the same implication is true for player 3 as well. If player 3 has to change the outcome, it has to change the median. So therefore it has to report a preference peak which is smaller than T2, and because of the single peak preference, this player likes that outcome much less than what it is happening currently. So player 3 is one who likes more hotter temperature, and any colder temperature is worse for him. So you can play around with this thing with more players, and you can see that whenever we are picking the median voting rule, so this is known as the median one. In particular, here in this example, we are discussing a few more extensions of the same idea. You can either pick the coldest temperature of this room, and that is also going to be strategy proof. So here, if the social choice function is going to pick the minimum, that is also truthful. You can You can see, think about that. Or maybe the hottest, that is also truthful. Why? You can use a very similar argument why the other players would not like to manipulate. If there is a hottest temperature that is being set, the players, the only way they can change is to make their preferences, their pick, to be even hotter than that. But of course these players will not like that temperature. They like the current temperature more than that hotter temperature. So just by looking at this domain restriction of the social choice function, we can actually circumvent GS theorem. And in the subsequent modules, we are going to prove a result about this domain.